Hello everyone. Welcome to another episode of Deep Dive Knowledge. Hello there. I read your article about fine-tuning LLMs and I found it quite interesting. I have a few questions regarding the techniques and their impact on generative AI development. Can we dive into that?
Of course. I'd be happy to answer your questions about fine-tuning LLMs and their impact on generative AI development. Please go ahead and ask your questions, and I'll provide you with detailed answers based on the information in the article.
Great. Let's start with the basics. In your article, you mentioned 3 ways to fine-tune a language model: self-supervised learning, supervised learning, and reinforcement learning. Could you explain each of these methods and their specific benefits in the context of fine-tuning LLMs?
In the article, 3 ways to fine-tune a language model are mentioned: supervised fine-tuning, unsupervised fine-tuning, and transfer learning. 1. Supervised fine-tuning. This approach involves training a language model using a labeled dataset specific to a particular task. The high-level steps for supervised fine-tuning mentioned in the article are: A. Choose a fine-tuning task, such as summarization, question answering, or text classification. B. Prepare a training dataset by creating input-output pairs and pre-processing the data. Tokenization, truncation, and padding. C. Select a base model and experiment with different models to choose the one that performs best on the task. D. Fine-tune the model using supervised learning. E. Evaluate the performance of the fine-tuned model. The benefit of supervised fine-tuning is that it allows the model to learn task-specific information from labeled examples. By providing specific examples of inputs and their corresponding outputs, the model can be trained to generate more accurate and relevant responses for the given task. Supervised fine-tuning is particularly useful when there is a specific task at hand and labeled data available for that task. 2. Unsupervised fine-tuning. Unlike supervised fine-tuning, unsupervised fine-tuning does not require labeled data. Instead, it involves training a language model on a large corpus of text without any specific task guidance. The model learns from the patterns and structures in the text data to generate coherent and meaningful responses. The benefit of unsupervised fine-tuning is that it allows the model to capture the general knowledge and language understanding present in the text corpus. It enables the model to generate responses that are contextually relevant and coherent, even without explicit task guidance. Unsupervised fine-tuning is useful when there is no specific labeled data available for the desired task or when the goal is to have a more general-purpose language model. 3. Transfer learning. Transfer learning involves using a pre-trained language model as a starting point and then fine-tuning it on a specific task or dataset. This approach leverages the knowledge and pre-training from the base model to learn task-specific information more efficiently. The benefit of transfer learning is that it enables the model to benefit from the pre-training on a large corpus of text. The base model has already learned the general language understanding, and fine-tuning allows it to adapt and specialize for a specific task. Transfer learning is particularly useful when there is limited labeled data available for the task, or when the base model has already been trained on a similar domain. Overall, the specific benefits of these 3 ways of fine-tuning in the context of fine-tuning LLMs include the ability to achieve better performance with fewer labeled examples compared to models that solely rely on supervised training. Fine-tuning allows LLMs to specialize for a particular task, generate more accurate and contextually relevant responses, and leverage the knowledge already captured in the pre-trained base models.
Thank you for explaining the 3 ways of fine-tuning LLMs in such detail. It's clear that each method has its own benefits and applications. I'd like to delve a bit deeper into supervised fine-tuning. In the article, you mentioned that supervised fine-tuning requires a labeled dataset specific to the task. However, labeling large datasets can be time-consuming and expensive. How can this challenge be addressed? And are there any alternative approaches that can be used to overcome the need for large amounts of labeled data in supervised fine-tuning?
The challenge of labeling large datasets in supervised fine-tuning can be addressed through a few different approaches. One approach is to use active learning, which involves selecting the most informative samples from the unlabeled data for annotation. This helps prioritize the labeling process and reduces the overall labeling effort required. By iteratively selecting the most uncertain or representative samples for annotation, active learning can effectively reduce the need for large amounts of labeled data. Another approach is to utilize transfer learning, where a model that has been pre-trained on a large labeled dataset for a related task is used as a starting point for fine-tuning. This pre-training stage allows the model to learn general patterns and knowledge that can be transferred to the target task during fine-tuning. By leveraging the pre-trained knowledge, the model requires less labeled data during the fine-tuning process. Additionally, there are alternative approaches to supervised fine-tuning that can overcome the need for large amounts of labeled data. One such approach is semi-supervised learning, which combines a small amount of labeled data with a larger amount of unlabeled data during training. The model learns from both the labeled and unlabeled data, leveraging the unlabeled data to learn additional information and improve performance. Another alternative approach is unsupervised learning, where the model learns from unlabeled data without any explicit labels. Unsupervised learning techniques, such as self-supervised learning, can train models to capture useful representations and patterns in the data without the need for labeled examples. These learned representations can then be used in downstream tasks, reducing the reliance on labeled data. Overall, by utilizing active learning, transfer learning, semi-supervised learning, and unsupervised learning, the challenge of labeling large datasets in supervised fine-tuning can be addressed, and alternative approaches can be used to overcome the need for large amounts of labeled data.
Thank you for explaining the various approaches to address the challenge of labeling large datasets. In supervised fine-tuning, it's clear that active learning, transfer learning, semi-supervised learning, and unsupervised learning can all help reduce the reliance on large amounts of labeled data. Now, let's discuss the concept of parameter training during fine-tuning. In the article, it mentions three options for parameter training: retraining all parameters, transfer learning, and parameter-efficient fine-tuning, PEFT, using techniques like low-rank adaptation, LoRA. Could you elaborate on these options and explain their benefits and drawbacks in the context of fine-tuning LLMs?
In the context of fine-tuning LLMs, the article mentions three options for parameter training: retraining all parameters, transfer learning, and parameter-efficient fine-tuning, PEFT, using techniques like low-rank adaptation, LoRA. 1. Retraining all parameters. This option involves training all internal model parameters from scratch. It is the most computationally expensive option but allows for maximum flexibility in adapting the model to a specific use case. However, a known issue with full parameter tuning is the phenomenon of catastrophic forgetting, where the model may forget useful information it learned during its initial training. 2. Transfer learning. Transfer learning involves leveraging the knowledge and pre-trained weights from a base model and fine-tuning only a subset of the parameters. This approach is computationally efficient as it avoids training the entire model from scratch. By building upon a pre-trained model, transfer learning allows for faster convergence and reduced reliance on large amounts of labeled data. It is particularly useful when the task at hand is similar to the pre-training task. However, transfer learning may still require a significant amount of labeled data specific to the target task for optimal performance. 3. Parameter-efficient fine-tuning, PEFT. Using techniques like low-rank adaptation, LoRA, PEFT techniques aim to reduce the computational costs associated with fine-tuning by selectively updating a smaller subset of the model parameters. One such technique is low-rank adaptation, LoRA, which approximates the weights of the model with low-rank matrices. This approach significantly reduces the number of parameters that need to be fine-tuned while preserving the model's performance. PEFT techniques can strike a balance between computational efficiency and model performance. However, it requires careful selection and adaptation of the model's parameters to ensure optimal performance. Overall, the choice of parameter training option depends on various factors such as computational resources, available labeled data, and the desired trade-off between performance and efficiency. Retraining all parameters offers maximum flexibility but comes with higher computational costs. Transfer learning is a computationally efficient approach that leverages pre-trained knowledge, but it may still require a substantial amount of labeled data. PEFT techniques like LoRA provide a balance between computational efficiency and performance but require careful parameter selection and adaptation. Each option has its benefits and drawbacks, and the choice depends on the specific requirements of the fine-tuning task.
Thank you for the detailed explanation of the options for parameter training during fine-tuning LLMs. It's clear that each option has its own trade-offs in terms of computational costs, performance, and the amount of labeled data required. Now, let's move on to the example code provided in the article for fine-tuning an LLM using LoRA. Could you briefly explain the key steps involved in the code and highlight any specific considerations or techniques used to ensure efficiency in the fine-tuning process?